Hello, I'm John Doherty. I'm the author of PEST. This video is the first of a series of two videos in which I try to explain some of the ways that you can get the most out of using PEST and the variables that control certain aspects of its behaviour that you can tune to optimize its use in different contexts. Let's start with the format of the PEST control file. This is described fully in the PEST manual. I refer you in particular to Appendix A of that manual, in which a table is presented in which the positions of all PEST variables in the PEST control file are outlined. This same appendix contains a summary of the meaning of each particular variable in the PEST control file. Now, in this video we're not going to be discussing every one of these variables by any means, just some of the variables which control the operation of PEST. In a PEST control file, a variable is located by the line on which it is written and by its position on the line. Some variables are essential, others, those indicated by square brackets, are optional. As we'll discuss shortly, there may be a new format for a PEST control file which is slightly more convenient than this, which will come into existence maybe in a couple of years, but for the moment this is the format that we have. So here's an example of a PEST control file in which the variable names which you saw before are now replaced with actual values for those variables. A PEST control file is divided into sections. Each section begins with a header. A header is identified by the fact that it begins with a star character, followed by a space, followed by the name of the section. Comments can be placed within a PEST control file. These must follow the hash symbol. Anything following that symbol is a comment and ignored by PEST. This comment can be at the end of a line. It can occupy the entirety of a line. Blank lines can be inserted anywhere within a PEST control file. If you're using PEST++, this is written by the USGS, PEST++ variables can also be included in a PEST control file. These are recognized by the fact that a line on which these variables are provided begins with ++. They can be placed anywhere within a PEST control file, but normally for convenience it's better to place them at the end of the PEST control file. PEST ignores these. Obviously PEST++ programs use them. Now here are the sections in a PEST control file. These are the sections that can exist in a PEST control file that is read by PEST or behaviour, and these sections are in a PEST control file that is read by PEST-HP, a more advanced and a version of PEST which is optimized for use in highly parameterized environments. There are some sections which can exist in one of these files but not the other. So PEST and behaviour can use derivatives command line section and a predictive analysis section, and a PEST-HP control file can include three sections listed here which are not used by PEST. If using PEST with these sections in the PEST control file, PEST will ignore them. Similarly, PEST-HP will ignore these sections. Some sections are optional and some are mandatory. The sections of a PEST control file that are written in bold letters in these figures must be in all pest control files. The other sections are optional. So here we have the variables in a control data section of the pest control file. You saw this table before. I've just split out the control data section of the pest control file. And here is an example of a pest control file with the present format. As I said before, each variable is recognized by the line on which it exists and its position on the line. Shortly, PEST++ will adopt a new format in which keywords are used to indicate the value of a control variable. Keywords that are omitted from the section of the pest control file are simply or variables for which the keyword is omitted from the pest control file will simply be provided with default values. In those sections of the pest control file, for example the parameter data section, in which information is supplied in tables, PEST++ will allow these tables to be supplied in external files, comma delimited files, which can then be built and edited using programs like Excel. As I said before, I may or may not program this into PEST depending on what other commitments I have to put new functionality into PEST and PEST HP. PEST has 4 fundamental modes of behaviour. The mode of behaviour that it implements on any particular run is set through the PEST mode control variable. This variable resides on the third line of a PEST control file, and it can be given one of 4 values. And these values are listed in this table. They're implemented as text, they're supplied as text strings to tell PEST how to operate on any particular model run, any particular inversion run. If PEST is run in estimation mode, then it is designed to solve a well-posed inverse problem. This is fully discussed in another video. In solving that inverse problem, it uses the equation shown here to arrive at a minimum error variance set of parameters under the supposition that the problem is well posed and hence that this matrix shown here can be inverted. So if we look at a simple 2-parameter space and we draw the contours of the objective function in that space, by saying that a problem is well posed, I am assuming that these contours close and that a unique minimum exists for that objective function. PEST task, when run in estimation mode, is to find that minimum. If PEST is run in predictive analysis mode, we still assume that we have a problem which is well posed. However, here its operation is slightly different. Normally, we run PEST in predictive analysis mode after we've calibrated the model, that is, after we've run PEST in estimation mode and found the minimum of an objective function that defines a well-posed inverse problem. PEST task, when run in predictive analysis mode, is to maximize or minimize the value of a prediction subject to the constraint that the model which we have previously calibrated stays calibrated. So, looking at our picture of objective function contours in 2-dimensional parameter space once again, we suppose that we have found this point here, the minimum of the objective function. Suppose that we deem the model to still be calibrated if the objective function is still below a value indicated by this contour, the inside of which I've coloured green here. Suppose now that these brown contours indicate the value of a prediction of management interest as it depends on our two parameters which define this inversion problem. PEST task then, when run in predictive analysis mode, is to find one or the other of these 2 points. These are the parameter sets which maximize this prediction or minimize this prediction, subject to the constraint that the objective function is at or below a certain user-supplied value. Then there is regularization mode. This too is described in another video. This is where PEST implements Tikhonov regularization to bring stability to an ill-posed inverse problem in which we may be estimating hundreds or thousands of parameters. When PEST is run in regularization mode, it employs two objective functions, a measurement objective function and a regularization objective function. PEST calculates a factor by which weights on the regularization objective function are multiplied, and it uses equations such as this to find a parameter set k underscore, which is of minimum error variance. In doing this, it actually solves a constrained minimization problem. The user specifies a measurement objective function which PEST is not allowed to go below. Then, subject to the constraint that the measurement objective function is no lower than that user specified value, PEST minimizes the regularization objective function and finds the optimal value of beta squared to achieve that. That is, maximum adherence to Tikhonov constraints while ensuring that we get the fit we want with the measurement data, but no better than that fit, because otherwise we'll overfit. This is explained in another video. When run in Pareto mode, PEST explores the interplay between two different objective functions. It could be used in a calibration context in which we formalize the interplay between the measurement and regularization objective function by traversing a so-called Pareto front. We may, for example, start off with 0 weight on the measurement objective function, slowly increase that weight, and find a point at which we think we've got a good enough fit but don't want to overfit. So we get to see in detail the interplay between maintaining Tikhonov constraints, adherence to Tikhonov constraints on the one hand, or seeking a good fit on the other hand, and we get to choose the place that we think is best along this so-called L-curve. Or we could use PEST in Pareto mode to undertake predictive hypothesis testing. We can start off with a calibrated model and then incorporate a specific prediction into the inversion process. We can start off with a weight of 0 associated with that so-called predictive observation, slowly increase the weight in order to see whether making that prediction happen causes us to misfit the calibration data set, and if so, what level of misfit we would incur for different values of the prediction. This may then allow us to identify the value of the prediction where it loses credibility because its eventuality causes too much misfit with the calibration data set. So that's when PEST is run in Pareto mode, it gradually adjusts the factor that it applies to one of the two objective functions that it is playing one against the other. So they're the 4 modes of operation of PEST, and all of them involve complex mathematical operations, involve inversion of what may be a very large matrix. And it's quite possible that the matrix that PEST is asked to invert is actually not invertible. For all modes of its operation except predictive analysis mode, to protect ourselves against numerical instability, we should always ask PEST to invert that matrix using singular value decomposition. This can be done simply by adding a singular value decomposition section to the PEST control file. The singular value decomposition section is fairly easy to fill. There's only 1, 2, 3, 4 control variables in it, and it's placed just above the parameter group section of the PEST control file. Except if you're running PEST in predictive analysis mode, you should always include a singular value decomposition section in the PEST control file. This gives you protection from numerical instability if PEST needs to invert a matrix which is in fact singular and can't be inverted. If we're undertaking that operation using singular value decomposition, PEST can still can do that operation, and it can do it in a way that accommodates the fact that it's being asked to invert a matrix that really is not invertible, and it can do this without any numerical penalty whatsoever. So now let's look at the contents of the singular value decomposition section of the PEST control file, and also the contents of a related section, LSQR. LSQR does virtually the same thing as singular value decomposition, but is able to do this thing better where the matrix which must be inverted is very, very large. So let's look at some of the details of these sections. Here are the specifications for the singular value decomposition section of the PEST control file. Let's start off by looking at this variable named SVD mode. Now, as was described in other slideshows, in other videos, PEST uses this equation to calculate a parameter set k underscore, which gives us the minimum error variance solution to an inverse problem. J is the Jacobian matrix, that is the matrix of sensitivities. Q is the weight matrix. If we undertake singular value decomposition on q to the half j, we obtain these matrices. U, an orthonormal matrix whose columns span model output space. V, an orthonormal matrix whose columns span parameter space. And S, a matrix of singular values. Alternatively, we could conduct SVD on JTQJ to obtain just this V matrix twice. If we set SVD mode to 1, PEST undertakes singular value decomposition on JTQJ and uses this equation to obtain our estimated parameter set. If we set SVD mode to 2, PEST undertakes singular value decomposition on q to the half j and uses this equation to come up with a minimum error variance set of parameters. Which is the best to use? It doesn't really matter. Perhaps use this if we've got large number of parameters rather than this. Turn SVD mode or set SVD mode to 0 to disable singular value decomposition altogether, in which case PEST will use another mechanism to invert this matrix. If there's no LSQR section, it will use a Gaussian elimination method, which is slow and cannot accommodate singularity of that matrix very well at all. However, if there's an LSQR section in the PEST control file, that could be used instead, as we'll discuss in a moment. Now, as we talked about in another video, when we undertake singular value decomposition, we actually truncate parameter space. We subdivide parameter space into a so-called solution space and an orthogonal complement to that, which is the null space. These variables on the second line of the singular value decomposition section inform PEST where that truncation must happen. Normally the best thing to do is set maxing, that's the maximum number of singular values, to the number of parameters that feature in the PEST control file, and thresh, that's the ratio of highest to lowest singular value, at a value of 5e-7. With these settings, we're not actually using singular value decomposition to do regularization. We're just using it to protect us against singularity of this matrix. Truncation takes place at that point where we can get maximum information out of the inversion process, but at a point that protects us from numerical instability should this matrix be non-invertible or nearly non-invertible. Then we let Tikhonov regularization actually take care of parameter sensibility, but we use singular value decomposition to give us unequivocal numerical instability, whether we have Tikhonov regularization or not, whether Tikhonov regularization gives us a numerical guarantee, a guarantee of numerical stability or not. So maxing, set it to the maximum, to the number of adjustable parameters. Thresh, set it to 5e-7. That protects us from numerical instability. Write, set it to 0. That just prevents the writing of an output file which can explain some of the details of the singular value decomposition process, but rarely are we interested in those details. Now, a problem with singular value decomposition is that it can get very slow if we have a lot of parameters featured in the PEST control file. There are a couple of ways that we can use to speed this process up. One is to use the MKL version of PEST HP. MKL is an Intel library that allows us to do matrix and vector operations very quickly indeed by parallelizing these operations on the computer on which PEST is operating. Another method is to use LSQR instead of singular value decomposition to solve the matrix equations that we saw in the previous slide, or do both of the above. Here's the LSQR section of a PEST control file. LSQR mode, set that to 1 to turn on LSQR. These other variables are a bit similar to the variables which appear in a similar position in the singular value decomposition section. The settings here normally work pretty well. See the PEST manual for further details. There is a mode of PEST operation which I refer to as SVD assist. This is related to singular value decomposition, but there are differences, and some people get confused about these differences. They are important, and I'll do my best to explain them to you right now. I do not recommend that you do SVD assist or undertake SVD assisted inversion unless you have to, but sometimes it is important because, for reasons we'll talk about in a moment, it can give you the ability to undertake inversion with a large number of parameters using a relatively small number of model runs. So, just a revision from another slideshow about what SVD, that is singular value decomposition, does for us. Singular value decomposition divides parameter space into two orthogonal subspaces. I refer to these as the solution space, and its orthogonal complement is, as is widely known, the null space. Now we then seek a solution to the inverse problem, which lies in the solution space. By doing so, the solution to that inverse problem is of minimized error variance. Because that solution to the inverse problem, which is K underscore in this picture, lies within the solution space, It can be viewed as the sum of vectors little v1, little v2, given to us as the columns of one of the orthonormal matrices that comes from doing singular value decomposition of the Jacobian matrix. The solution to the inverse problem is alpha times little v1 plus beta times little v2 to give us k underscore. So when we use singular value decomposition in a PEST control file, every iteration of the inversion process goes like this. First, we calculate a full Jacobian matrix by running the model as many times as there are adjustable parameters featured in the PEST control file. Then we undertake singular value decomposition of that matrix. Through doing that, we define little v1, little v2 that span the solution space. Using a little bit more of the mathematics of the matrices that emerge from the singular value decomposition process, we calculate alpha and beta, and finally calculate k underscore, and then we repeat that entire process during every iteration of the inversion process. Now, I'm going to refer to little alpha, beta, etc. as superparameters. The final solution to the inverse problem, k underscore, as I just said, is the sum of each one of these superparameters multiplied by a vector given to us through singular value decomposition. The final k underscore is a function of these superparameters applied to this orthonormal matrix which emerges from the singular value decomposition process. Now, if we're using SVD assist, and this is a special way to set up a PEST control file, this is not done by you, it's done by a special PEST utility, which we'll talk about shortly. But if I'm going to undertake SVD assisted inversion, I use the principles of singular value decomposition, but I apply them in a different way. If we're going to undertake SVD assisted inversion, then we need to have a SVD assist section in the PEST control file. We don't have to put this in ourselves, it's put in by a special utility called SVDA prep. But before we even start on the inversion process, we use singular value decomposition to calculate these little v1, v2 vectors which define the solution space. So we break the functionality of singular value decomposition into two parts. First, before we even start estimating parameters, we have a PEST control file that's constructed in the normal manner. It'll feature normal, so-called base parameters, the parameters that the model sees, the parameters that we see. We run the model npar times, where npar is the number of adjustable parameters, and we calculate a Jacobian matrix. We undertake singular value decomposition on that matrix. That defines little v1, little v2, etc. That's done before we start the inversion process. Then we run a utility, which you'll see in a moment, to calculate a new PEST control file featuring superparameters. Everything is automated. During every iteration of the SVD assisted inversion process, PEST then retains the original null space solution space subdivision that was defined during the original singular value decomposition. PEST then works entirely with superparameters. During every iteration of the SVD assisted inversion process, when it runs the model to build a Jacobian matrix, when it varies each parameter incrementally in order to fill that matrix, It doesn't vary the base parameters anymore, it varies the super parameters. That means it varies the base parameters in combinations defined by the components of little v1, little v2, etc. Because it's only estimating super parameters, and because it's calculating a Jacobian matrix based only on super parameters, the number of model runs required per iteration is vastly reduced. Hence, we can estimate a k underscore with a very much less number of model runs than we would use if we did a full Jacobian matrix every iteration. We do not do a full Jacobian matrix every iteration. We just calculate a Jacobian matrix based on super parameters. Those super parameters are defined as an outcome of one great big Jacobian calculation based on real parameters, native model parameters, base parameters. So just a few notes on SVD-assisted inversion. Obviously, it's cheap, much cheaper than normal inversion. And also, just to make it even cheaper, that first iteration of the SVD-assisted inversion process we get for free. We don't have to actually do finite difference derivatives based on superparameters. The derivatives of superparameters are calculated from the base Jacobian matrix, the same matrix that allows us to define superparameters in the first place. If we have Tikhonov regularization in the original PEST control file, based on base parameters, that is still employed as a regularization device when we do SVD-assisted inversion. The same Tikhonov constraints are applied to base parameters as are applied in the initial PEST control file, even though we're calculating derivatives with respect to superparameters. So, the whole thing is very efficient, but of course, nothing comes without a cost. Because we're working with superparameters, and because those superparameters were defined only once at the start of the inversion process, if the model is nonlinear, then that subdivision of parameter space into solution and null spaces that we did at the beginning of the inversion process may not be applicable throughout the inversion process. It's possible then that the solution we obtain to the inverse problem by doing SVD-assisted inversion may not be optimal, in that it mightn't be the minimum error variance solution to the inverse problem. It may have a little bit of bias. It may not look as nice as one we would have obtained if we hadn't undertaken SVD-assisted inversion. The fit with the calibration data set may not be quite as good. Also, there can be some little numerical problems if parameters hit their bounds. Hence, I don't use SVD-assist unless I have to. But there are occasions when I have to, because I just don't have enough computing resources to handle a large number of parameters and a slow-running model. There will be many times when this is the only option. But if you can avoid it, do avoid it. But if you do use it, then use as many superparameters as you can. Use SVD to estimate those superparameters. We'll see how to do that in a minute. Or if you've got lots of parameters in the base PEST control file, use LSQR to define the superparameters. Or use the MKL version of PEST-HP if you have many base parameters. That can also speed up the definition of superparameters and the inversion process. So, if we're doing SVD-assisted inversion, we will have a PEST control file with an SVD-assist section in it. We do not have to write this, it's written for us automatically. That file should still have a singular value decomposition section in it. This will be inherited from the base PEST control file, As we spoke about a little while ago, you should always use singular value decomposition as your solution device. If that's in the base PEST control file, the SVDA prep utility which writes the super parameter PEST control file will transfer this section from the base parameter control file to the super parameter control file automatically. And if you have too many super parameters to formulate a well-posed inverse problem, that's fine. Singular value decomposition will keep the inversion process stable. And in general, we should have as many super parameters as we can. The more super parameters we try to estimate, the more we defend ourselves against the effect of that linearity assumption that I spoke about a moment ago. So the workflow is rather simple. We set up a PEST control file. We don't even think about SVD assisted inversion as we're setting up a PEST control file. We have a singular value decomposition or LSQR section, just as we normally would for reasons that we just spoke about. We add Tikhonov regularization to give us a solution to the inverse problem in which parameters are sensible and which is a minimum error variance solution to that problem. We'll talk shortly about easy ways to add Tikhonov regularization to a PEST control file. Once we've done that, we set the noptmax variable in the control data section of the PEST control file to -2. This is a termination criterion, number of iterations that we should undertake. By setting nopmax to -2, we are telling PEST, don't solve the inverse problem, just run the model as many times as there are adjustable parameters, calculate and store a Jacobian matrix, then stop. Next, we run this utility called SVDA prep. It builds us a superparameter PEST control file. It inherits as much as it can from the base parameter PEST control file, including Tikhonov regularization if it's present, but the whole inverse problem is redefined in terms of superparameters. The original model batch file becomes a new batch file which includes the wherewithal to back calculate base parameters from superparameters so that we actually are still estimating parameters used by the model. The superparameter estimation process is concealed from our view. Once we've run SVDA prep and set up PEST for SVD assisted inversion, if we're using PEST or PEST HP, we copy all the files to the folders in which the parallelization agents are working. Then we run PEST. PEST stores parameters in a file called case.par, where case is the name of the SVD assist PEST control file. Let's call that case_svda.par. But the parameters that we want, the base parameters, are stored in a file called case.bpa, which is named after the base parameter PEST control file. So base parameters estimated via superparameters are always available to us in this file. At the end of the inversion process, we then use a little utility called parap. Parap stands for parameter replacement, to build a new base PEST control file using parameters that we've just estimated through SVD assisted inversion. It's all described in the PEST manual, and it's not that complicated, and the savings in the number of model runs can be very large indeed. Here's a screenshot of running the SVDA prep utility. For most of the questions that it asks you, you can simply hit enter for default. How should you define superparameters? Using singular value decomposition or LSQR? Either is fine, but if you've got too many parameters in the base PEST control file, choose LSQR. How many superparameters should you estimate? Well, there's a little utility called SoupCalc supplied with PEST, which will estimate how many dimensions are in the solution space. Use as many as it suggests. It gives you a lower bound and an upper bound. Use as many as it provides for the lower bound, but actually estimate as many as you can, but try to make sure it's above the SoupCalc suggested lower bound. By estimating as many as you can, as I said a moment ago, that gives you some defense against the linearity assumption involved in the once-only definition of superparameters. The answer to most of the other questions, just hit enter. The defaults are fine. And that, in a nutshell, is how to undertake SVD-assisted inversion. The important point here is to distinguish between SVD-assisted inversion and singular value decomposition. Always include a singular value decomposition in the PEST section in the PEST control file. Only undertake SVD-assisted inversion if you have to. So now, let's look at some easy ways to add Tikhonov regularization to a PEST control file. Recall from other videos the way that Tikhonov regularization works in PEST. When run in regularization mode, PEST actually solves a constrained minimization problem. It works with two objective functions, one called the measurement objective function, the other called the regularization objective function. It balances the two through this factor applied to the regularization objective function, which I've denoted here as beta squared. The user supplies a target measurement objective function. If PEST can achieve that target, it will, but it will not reduce the measurement objective function below that target. In maintaining that target, it then reduces the regularization objective function to as low a value as it can, that is, respecting Tikhonov constraints as closely as it can. It minimizes the regularization objective function subject to the constraint that the measurement objective function adopts a user-specified value or approaches that value as closely as it can. Now, how does PEST know which observations or prior information equations enforce Tikhonov regularization? It recognizes them because they belong to observation groups whose name begins with REGUL. And both prior information equations and observations can belong to an observation group whose name begins with REGUL. These are the groups to which this so-called regularization weight factor is applied. This factor is recalculated during every iteration of the regularized inversion process. So, to run PEST using Tikhonov regularization, the PEST control file has to have a certain number of things in it. The PEST mode variable should be set to regularization. One or a number of observation or prior information groups must have a name that begins with REGUL. And the PEST control file must have a regularization section. That section contains control variables, which control the way that PEST applies regularization constraints. It contains the target measurement objective function, variables which control how beta squared is calculated during each iteration of the regularized inversion process, and some other optional and non-optional regularization control variables, some of which we'll mention in a moment. Now, the easiest way to add regularization to a PEST control file is through use of a two utilities supplied with PEST. The names of these utilities are addreg1 and addreg2. Their use is based on the premise that we have a PEST control file which contains no regularization, in which PEST mode is set to estimation. By running these utilities, a new PEST control file is automatically built in which PEST mode is set to regularization and in which one prior information equation is added to the PEST control file for every parameter featured in the parameter data section of the PEST control file. Then a regularization section is added to the bottom of the PEST control file. So here is part of a PEST control file built by addreg1. Firstly, PEST mode becomes regularization. Here is the parameter data section of the new PEST control file. This is identical to the parameter data section of the original PEST control file, but the initial values in the parameter data section are particularly important. addreg1 enforces or builds a PEST control file which enforces so-called preferred value regularization. Each parameter is endowed with a preferred value that is equal to its initial value in the original PEST control file. So those values should be chosen wisely. In the parameter data section of the original PEST control file, as in any PEST control file, each parameter is assigned to a parameter group. Parameter groups are listed in the parameter group section of a PEST control file. As we discuss later in this video and in other videos, the parameter group section of the PEST control file contains variables which describe how finite difference derivatives should be calculated by PEST. When we're using addreg1 or addreg2, these groups have a secondary role. Prior information equations that enforce preferred value Tikhonov constraints are assigned to prior information groups. Any constraint which is applied to any parameter is assigned to a group whose name is named after the parameter group to which the parameter belongs. So, the prior information equation, which expresses a preferred value for this parameter here, is assigned to a group that is named after the parameter group to which this parameter belongs. This has a couple of repercussions. The name of any regularization group must begin with regul. To name the regularization group to which these new prior information equations belong, addreg1 affixes the name regul to the parameter group. Therefore, this parameter group should have a name which is 6 characters or less in length. That leaves room to add the regul underscore prefix to the observation group to which prior information equations are assigned. It's also wise to assign parameters of different types and in different parts of the model domain to different parameter groups so that they can be assigned to different prior information groups. This has importance for reasons we'll talk about in a moment. Hence, for example, pilot points in layer 1 of a groundwater model should be assigned to one parameter group. Pilot points in layer 2 of the same groundwater model should be assigned to another parameter group, even if the variables which control calculation of finite difference derivatives are the same for both groups. The prior information equations pertaining to these different parameters in different layers will be assigned to different regularization observation groups. This allows PEST to exert differential weighting on those prior information equations. This can add stability to the Tikhonov regularized inversion process. Here is an example of the prior information section of a PEST control file written by adreg1. Each prior information equation must have a name. Well, that's named after the parameter to which it pertains. If a parameter is log transformed in the parameter data section of a PEST control file, the prior information equation pertains to the log of the parameter. So does the preferred value. And here is the name of the observation group to which prior information equations are assigned. regul underscore affixed to the name of the pertinent parameter group to which the parameter belongs. In the regularization section of the PEST control file, which is written by adreg1, the target measurement objective function is set to a very low value. Now you can change that if you want, but adreg1 tells PEST to aim very low. But meanwhile, it sets this variable here, frac_phi_m, to a value of 0.1. That says that at any stage of the regularized inversion process, the target measurement objective function is in fact 0.1 of the value of the current measurement objective function. So regularization is always operative, it's always visible in the inversion process, even though at the end of that process, PEST will do whatever it can to get the lowest measurement objective function that it is possible to get. Also, adreg1 assigns a value of 1 to this regularization control variable named iregAdge. This variable tells PEST that it can exert differential weighting on different regularization groups. This can often be useful. There are a number of values that iregAdge can have, and this governs the way PEST assigns that differential weighting. What we ideally would like for higher regularization weights to be ascribed to groups for which there is little information in the calibration data set pertaining to the parameters which the groups describe. Conversely, where the information content of the calibration data set is rich with respect to other parameters, the regularization weight factor should be lower. Normally I set iregAdge to 1. That's the value that adreg1 assigns to the iregAdge variable. Finally, in the observation group section of the new PEST control file, the names of the new observation groups, these are the groups to which prior information equations are assigned, these are recorded in the observation group section of the PEST control file. To run many of the utilities that are supplied with PEST, just type their name. If you don't know how to do it, just type their name at the command prompt, and then the utility will tell you how to run it. If you type the name adreg1 at the command prompt, this is what you'll get. If you type the name adreg2 at the command prompt, you'll get a slightly different instructions on how to run adreg2. adreg2 allows you to have some input into what appears in the regularization section of the PEST control file. As I just said, adreg1 applies default values to all entries in the regularization section of the PEST control file which it writes. If you use adreg2, you have the ability to set the target measurement objective function through the command line. This other variable, phi_m except, is set slightly above this phi_m_lim, the target measurement objective function. Optionally, adreg2 allows you to set a value for frac_phi_m, though 0.1 is often the best value for this variable. adreg2 also allows you to set a value for iregAdge, but as I said previously, a default of 1 is often fine. You don't have to provide values for these on the adreg2 command line. This is optional. Now there's another variable which you may consider using in the regularization section of a PEST control file. This is placed into that section by neither adreg1 nor adreg2. The name of this variable is regContinue. The way PEST works when running in regularization mode is that if the target measurement objective function falls below, if the current value of the measurement objective function falls below the target, PEST will cease execution as it's done its job. You have attained the target measurement objective function that you asked for. However, if you set this regContinue variable to continue, PEST will continue with the regularized inversion process. It will then try to raise the measurement objective function back up to the target, because this then gives the ability to minimize the regularization objective function to the lowest possible value that it can achieve, thereby paying maximum respect for regularization constraints. In some circumstances, this can be useful. It's worth noting too that in many circumstances, especially in calibrating a groundwater model, you should add covariance matrices to accompany the names of the observation groups which adreg1 and adreg2 list in the observation group section of the PEST control file. As is explained in the PEST manual, if you add the name of a file containing a covariance matrix to a PEST control file immediately following the name of an observation group, including a prior information group, then PEST doesn't use weights for that prior information or observation. It uses a covariance matrix instead, applied to the whole group. Now, if our parameters are spatial parameters, for example pilot points, then by adding a covariance matrix, by using covariance matrices instead of weights applied to the whole group, the parameter fields that emerge from the inversion process can be much nicer than if we don't. If we don't use a covariance matrix, we tend to have point-by-point parameterization. It looks ugly, it's not geologically realistic. By using utilities such as ppcov and the others listed here, which are supplied with the groundwater data utilities, which can be downloaded from the PEST website, by using covariance matrices built on the basis of variograms or even spatially varying variograms, the parameter fields which emerge from the regularized inversion process look a lot nicer. They are more in harmony with the geology at that site, the site of the groundwater model that you're calibrating, if the information supplied to these utilities reflects the prevailing geology. The parameters will look much nicer, the parameter field will be much smoother, and you won't have a bumpy, lumpy type parameter field that doesn't look geologically realistic at all. This is discussed in another video. So what's the best strategy to apply when using Tikhonov regularization in a PEST control file? Well, this is something that's up to the individual. I will always, if I'm calibrating a groundwater model, use covariance matrices with the prior information equations that adreg1 or adreg2 adds to a PEST control file. Often I'll use adreg1. I'll tell PEST, get the lowest measurement objective function that you can. But because fracphi-im is set to 0.1 and iregAdge is set to 0.1, I still get a reasonable parameter field, but I have probably overfitted. But I find out the best fit that I can get. And if it's not good enough, then perhaps my model's not good enough and needs some conceptual refinement. However, I'll often find that I've overfit a little. Then I will run PEST again, in regularization mode, but now I know what to set the target measurement objective function at. I set it about 5% higher than the best I could get when I aimed very low. It's often in that last 5% of fit, trying to achieve that last 5% of fit, that the parameter field gets really ugly. By aiming slightly above the best I can get, I can still get a pretty good fit with the calibration data set, but I can achieve it with a much nicer parameter field. So by running PEST first with a very low target measurement objective function, and then running it with a target measurement objective function that is slightly above the best I can get a good fit and a reasonable parameter field. Finally, if you want to get rid of regularization from a PEST control file, use the subreg1 utility. This is something I often do after I've calibrated a model, but before I do the uncertainty analysis, because when we do uncertainty analysis, this is where we abandon regularization, which gives us a minimum error variance solution to the inverse problem. That is, a solution to the inverse problem with only as much heterogeneity as the data can support. That's all right for calibration, but for uncertainty analysis, I actually am looking for heterogeneity, the heterogeneity that may exist and that is compatible with the geology, and by expressing that heterogeneity in a stochastic sense, I get to explore post-calibration uncertainty of any predictions made by my model. But that's a subject for another video. This brings us to the end of part 1 of this series of 2 videos.